Hi, I'm Scott Simpson, and today we'll be talking about significant figures. So a lot of times people really aren't too sure why significant figures are important. The important point behind them is that they're meaningful digits. So if you take a measurement and you want to report that value, what can you reliably report to? An example I constantly use is driving around using a car odometer. We could use satellite data to get down to like the inch at which we need to go in terms of a distance. But how is that actually useful if you have a car and your car only measures in like maybe a tenth of a mile if it's a good odometer? So there are a set of rules that are associated with these significant figures, and that's what we're going to talk about today. So let me get to my camera. There we go. So there are some basic rules that are followed when determining the number of significant figures. So we're going to shorten significant figures to sig figs, and we're going to state the rules. The very first rule is non-zero digits are significant. So as an example, if I have the number 1,141, and if my camera will focus, that number itself has 4 significant figures. Each one of these digits counts. Second rule, any zeros between 2 non-zero numbers are considered significant. So zeros between 2 non-zeros. Digits are significant. So for example, if I have the number 1001, there are 4 significant digits in here. These zeros are significant because they're wedged between 2 non-zero digits. So 4 sig figs. Rule 3 has to deal with zeros to the left of the first non-zero digit. So zeros to left the first non-zero digit are not significant. So as an example, let's say we have 0.00121. That value there. If we consider the number of significant digits, these zeros are not considered significant, whereas these digits on the end are. So this number, they have 3 sig figs. The fourth rule has to deal with zeros to the right. Zeros to the right of any non-zero digit are considered significant. So zeros to right of non-zero digit are significant. So we're going to work off of our last example. Let's say we had this number, but we tacked on an additional 0 on the end. Now, if we consider the number of significant figures, these ones don't count. However, all of these digits do. So this number would have 4 sig figs. The final rule has to deal with ambiguity or trailing zeros. So trailing zeros are ambiguous, meaning they can have a variable amount of significant figures. So as an example, if we had the number 300, there are actually 3 answers for the number of significant figures here. We could have either 1, 2, or 3. We're not really sure because the person who wrote this number down didn't indicate the significance. So what's always a good idea is to convert everything to scientific notation. So if we wrote 3.00 times 10 to the second, that number has 3 sig figs. Whereas if we just wrote 3 times 10 to the second, that number would have 1 significant digit. All right, so now that we know how to determine the number of significant digits in each number, we have to move to different mathematical manipulations and how that influences our significant digits. The easier operations to keep track of sig figs is actually multiplication and division. So let's talk about that one first. Multiplication, and division. So in this one, our answer is going to have the smallest number of significant figures of the 2 original numbers, or of the series of original numbers that we are multiplying together or dividing. Answer has smallest number of sig figs of the original numbers. So as an example, if we take 12.0 and we multiply it by 43.01, let's just evaluate this mathematically first, spitting out all digits, and then we will determine how many sig figs our answer should have and what's the value we should report. So we multiply this through, you'll end up with 516.12. Now, let's look at the sig figs of our original numbers. This number here, remember, zeros to the right are considered significant. So this has a pen that doesn't work. Try this one. Better. 3 sig figs. Whereas this number, there's a 0 wedged in between 2 non-zero digits. This guy has 4 sig figs. Therefore, our answer should have 3 significant figures. So we have to approximate this to 3 sig figs, keeping rounding rules in mind. Remember, 5 or higher, you go up, 4 or lower, you go down. In this case, we would report 516 as our answer. Okay. But what about addition and subtraction? Addition and subtraction has nothing to do with the original amounts of significant figures, but we are keeping track of digits after the decimal. So addition and subtraction. In this case, our answer has smallest number of digits after the decimal of our original numbers. A common place students mess this up is they think the number of sig figs of the original numbers is how you do this. No, it has to deal with the digits after the decimal. So to prove this to you, we're going to look at this example. We have 9.55 plus 0.755. Okay, let's evaluate this numerically. We add these portions up. And that is our result. Now, the rule says we have to go to the smallest number of digits after the decimal point. So if we keep track of that, this is the point at which we need to truncate. So let's approximate this value. So we get 10.3, and remember, since there's a 5 next to it, we have to round it up to 1. Now let's consider the significant figures of each of these numbers. This first number has 3 sig figs. Second number also has 3 sig figs. But our result has 4 sig figs. So with addition and subtraction, you can even move up in terms of the number of significant digits or move down in terms of the number of significant digits. You really have to pay attention to how many, like how far are you going, how many decimal points do you have past this point. Okay, the final rule has to deal with something called exact numbers. So exact numbers are numbers that are set up by definition that have an infinite amount of significant figures, or if you know them exactly. For example, like if you have two apples on a desk sitting there, you have the number 2 exactly, 2.00 repeating. So it has an infinite amount of significance. Whereas there are some other numbers that are set up by definition to have a large number of sig figs. So definition that have an infinite amount of sig figs. So as an example, consider how many grams are in a kilogram. For every 1 kilogram, there are 1,000 grams. Or for every 1 kilogram, there's 1 times 10 to the third grams. Looking at these numbers, it looks like each of them has one significant figure, but knowing that exactly 1 kilogram is equal to exactly 1,000 grams, what this is really implying is 1.000 so on kilograms is equal to 1.000 repeating times 10 to the third grams. So in reality, there's an infinite amount of significant digits in these numbers. So with that, I would like to thank you for watching. If you have any questions or comments, please leave them below. Thank you.